Hey everyone, welcome to our Physics 30, and it's been a while since we did some physics, so I'm going to pick up where we left off. EM number 6, we're going to deal with electric field lines. Just as a refresher, here is our symbol for the electric field, an E with the arrow overhead. And to start, I kind of just want to go through some rules with you guys. The first being that electric field lines extend away from a positive source charge. And I wrote extend away from a positive source charge. Just extend away from a positive source charge. This kind of makes sense. The electric field is represented by what actually would happen when a positive charge is placed near that object. So what happens when a positive charge is placed near a positive source charge? Well, they should want to repel each other. So if I place the positive charge here, it should want to move away from this positive source charge. Along that same line of logic, field lines extend towards a negative source charge. So if I placed a positive charge here, our test charge, it would want to move towards the negative charge. The last rule is that the strength of the electric field, or the magnitude, these are the same idea, the magnitude is represented by the density of lines, or quite simply how many lines you draw. And so a stronger electric field than the one represented here would be one with more lines. Okay, that's kind of how that we represent magnitude. Our third example is kind of where we'll begin, and we want to draw the field lines not just by the individual negative charge, but what happens when there are two of them near to each other. What would happen to a positive charge placed in different areas in this region? So we draw our lines kind of as what would kind of happen. And so for the most part, these regions are pretty easy to draw. Everything behaves fairly similar to an individual charge in this localized region, and same here. It's when you get into regions where both charges can influence that positive. So for example, in this region, normally it would want to go like this. But since it's getting pulled by this other charge as well, it's kind of going to go like that. It's going to have a little bit of a curve to it. Same right here. And we can do the same right here. So that would be kind of the trajectory that a positive charge might follow. Right in the middle here, you might think that a positive charge, it's going to want to go to the left, it's going to want to go to the right, but these two charges will pull equally on that positive charge, and therefore right along that equatorial, there will be no electric field there. So we can leave that blank. Okay. That's the basics of drawing field lines, and now we have a few shapes, I guess is kind of how we would say it, that we want to explore the concept of what would happen with the electric field for these different shapes. So the first shape we want to look at is a solid conducting sphere. So what kind of getting at here is, let's say we have a sphere, it is solid and it will want to conduct electricity. So let's say we do have some charge. If it's neutral, it's not going to want to conduct, so we must have a buildup of one type of charge somewhere. So kind of explore the negative charge on the sphere. So let's say we have a distribution of charge. The very first kind of concept with this is along this particular surface, the charges distribute evenly. The charges distribute evenly on the surface of the sphere. And throughout this, I'm very much asking the question, well, why would they want to do that? And we're thinking back to the fundamentals that, well, this is a negative charge and that's a negative charge. So they're going to push on each other. And the same with that negative charge. And in fact, all three are going to push on each other. And so by saying they distribute evenly, we're saying they're all pushing on each other. And they're going to come into a kind of like an equilibrium. And so that equilibrium will be the charges evenly being located at different distances, or they're going to be located the same distances away from each other. That's the idea of distributing evenly, because they all push on each other. Due to that electrostatic force. So that's where the pushing comes from. So we'll redraw our sphere here. I guess this represents what the electric force would do. They're going to kind of push onto each other, same amounts. And so here we represent what the electric field would do. And so first things first, let's actually draw them being evenly distributed along the surface of the sphere and say, okay, well, how does a field line behave? How would we draw that? So let's draw right here, which you can't see, so let me put my paper up. Yeah, so let's draw right here. So at that point, a positive charge will point directly to that negative charge. And right along this point, this negative charge is going to bring that towards it. You guys can see that line. Actually, when I do that, so that negative charge is going to want to bring it towards it, but so will that other negative charge that's over here. And so what ends up happening is your electric field still points straight down. And we can do this everywhere on the sphere. And it turns out that for this solid conducting sphere, regardless of the amount of charge that's distributed, the electric field will always be perpendicular to the sphere at any point on the sphere. So all electric field lines are perpendicular to the surface. Okay, so that's the first object that we're going to look at, followed by the irregularly shaped solid conducting object. So a sphere is very nice, it's very uniform, it's very symmetric. What happens when we have a solid object, solid conducting object, which is not so symmetric? So here's kind of the example we're going to look at. So here's our regularly shaped object. And to get this kind of concept across, I want to look at two particular points. I want to look at a distribution of charge along the bottom here. I want to look at a distribution of charge along the top. So what happens at the flat surface? What happens at this curved surface? And so I'm going to label those location 1 and location 2. Location 1 is the easiest to kind of look at. So what will these two charges look to do? And so we're kind of just talking right now about the electric force between all of the objects. So this charge will push this one along that way, and vice versa. These like charges will repel each other, and so they're going to want to spread out quite a bit here. So that's location number 1. So this push is along the surface. And location number 2 is a little different. So location number 2, it's still going to be kind of capable of doing that. However, these two charges more or less push kind of outwards this way. Having bad luck with pencils, actually. They're going to push this way. And so they're still pushing on each other, but that push is less along the surface. Just less along the surface. And so what does that mean for our object? Well, that means that if they're not pushing along the surface of the shape as much as down here, they're going to be able to actually kind of come a little closer to each other. They're going to kind of densely be packed at these curved areas. And that's actually kind of what we see. So the electric field lines, which we'll draw next, for our object, are going to be pointing towards our negative charges here. And that makes sense. However, along the curved surfaces up here, the charge will be allowed to kind of pack more densely, and so our field lines will also be much more dense. lines is able to be seen in quite a few different places in nature. One of really, really common examples of this was a long time ago on ships, where the masts were these metal objects that were very pointy, and so they called it St. Elmo's fire. And it's kind of the image that's at the beginning of electric field line chapter in your book. And sailors would often be able to see this phenomena by the green or bluish glowing light along the masts, or the tips of the masts of ships. The other place that this effect can be seen would be on airplanes. They're not so symmetric, and so you'll be able to see a buildup of charge there as well. Okay, so that is our second object. Next up, we have a hollow conducting. The particular shape we'll use is a sphere. However, this is the case for any hollow conducting object. It kind of works a little bit like this. So let's draw our hollow sphere as best as we can. And imagine that we have some charge built up. What we'll find is that in this case, no matter what the object, the charge accumulates on the outside only. The outside surface only. There will be no charge buildup on the inside. So the electric field, therefore, it's actually quite similar to our sphere that we just drew, and the concepts are exactly the same. The charge will push on each other, evenly distribute. All electric field lines will point perpendicular to that spherical surface. And the key idea being that inside the conductor, the electric field is zero. Inside the conductor, the electric field is zero. This is quite an interesting phenomena. It has a really nice special name called the Faraday cage. Practical application being perhaps an airplane. Airplanes are Faraday cages. And what this allows is any charge that is along the outside can't actually get inside. Any electric discharge will have no interaction inside because there's no electric field strength on the inside. So that's our third object. Our last object that we want to look at is a flat, solid conducting plate. Flat, solid conducting plate. So let's draw one of those here now. So we have a bunch of positive charge, for instance, on a flat plate. And so what will other positive charges want to do? Well, first off, they're going to evenly distribute, so that's very key. That's kind of like a common theme here. Charges push on each other. And here, you're going to have the electric field point away from that positive charge. And similar to what we drew previously, right along here, well, this is going to kind of go like that. That's going to be the way that this positive charge influences something placed right here. This will push it directly down, and this positive charge will push it kind of like that. And you see a lot of symmetry with that dotted line and this dotted line, and so they kind of cancel out. And so therefore right here, it also points directly down. And the nice thing about a solid conducting plate is that that repeats all the way along the length of the plate until you get towards the edges, which the electric field's kind of going to bounce outside of that region. So the edges are a little different, but everywhere in the actual inside the plate points directly down. This is important. In this region, it is a uniform electric field. And we actually have a pretty good application for this because we have a positively charged plate, and we throw on the other side a negatively charged plate. And how would this change our electric field lines? Well, negative charges would like things to go towards them, and so this doesn't actually change all that much. It wants to do exactly what we see here. And so this actual particular diagram that we drew for one plate is also the same for two. It would just perhaps be a little stronger, which we'll draw with more lines. A stronger electric field. It's more charge. So this actually has a fancy name. This is called a parallel plate capacitor. Or perhaps just called a capacitor. That's where we'll stop this for now and continue on with the next